So we're going to start with where we stopped off last class. So this is the beginning of our distance learning little journey that we're on. So hopefully you can hear me and you can see the screen really well. Let me know. I'm going to post this video early so you can let me know if it's not working or if you're having issues with it. So last class we wrote out the Arrhenius equation, which was K is equal to A, big A, E to the negative EA over RT. We said K was the rate constant, big A was my frequency factor, like the orientation. EA was my activation energy. R was my gas constant, the 8.314. That's just going to be on the back of your periodic table. And T is your temperature in Kelvin. Now, this isn't necessarily the most useful equation the way it is. So what we want to do is we want to rearrange it so that it can be more in a line equation, like a y equals mx plus b. So to do that, we want to take the logarithm, natural log, of both sides. So we have our K is equal to A e to the negative EA over RT. So we take the ln of both sides. Okay. Now, one of the rules of natural log is ln of AB is equal to ln of A plus ln of B. So what that means is I can take this side, if this is A and this is B, I can separate it out. So ln of A plus ln of E to the negative EA over RT. Now, we also know that if you take ln of the E of something, that we can rewrite this. We can take this EA RT and it actually comes down and goes in front. So ln of K is equal to ln of A plus negative EA over RT ln of E. Now, ln of E is just 1. So we get ln of K is equal to ln of A plus negative EA RT, and this just went to 1, so times 1, which we can just leave the way it is. Okay, now we also kind of want to rewrite this because I want the x-axis to be 1 over t. So if we're trying to do a y equals mx plus b, let me write this guy since it's got my t. Let me put him first. So ln of k is equal to, and let me take the t out. So I have my m and my x. So it'd be negative EA over r, 1 over t, plus ln of a. So this is my y, my ln of k. This is my m. This is my x, and then this is my plus b. So y is ln of k. My slope, this is the part that we really wanted to get from this. The slope is equal to negative EA over r. This is going to be really helpful. Okay? My x is 1 over t, and my b is ln of a. Now, you might be saying, I do not follow that at all, Dr. C. I'm so confused. What you need to take away from this is 2 things. You don't need to memorize this whole thing. The 2 things that you have to know is that the slope is equal to negative EA over r, so we need to know this. And we need to know that the y-intercept is equal to ln of a. That's the stuff you need to take away. So if you are watching this and you're completely confused on like how to go with the natural log and all those rules for all of that, don't freak out, don't stress. Just know the y-intercept is ln of a and that the slope is negative EA over r. And I'm going to show you a problem of how this is useful, okay? So here's the problem. It's the iodide methyl bromide reaction that we talked about with our orientations. And on the x-axis is 1 over t. The y-axis is ln of k. And so here I have the intercept and I have the slope. the first thing I want to know, my first question mark for this is I want to know what EA is. And then the second question mark is I want to know what A is. All right, so if I'm looking for EA, if I'm trying to find EA, they gave me the slope and they gave me the intercept. So I have to know how the slope and the intercept relate to my activation energy. So this is where we have to go through and go, okay, slope is equal to negative EA over R, and my intercept is equal to ln of A. Okay, so whenever I have, now I know I have those, now I can just plug everything in. But this is the two you have to know. You have to know the slope equation here and the intercept. And how you know you're going to use these is because I gave you the intercept and the slope. And this is ln of K, and this is 1 over T. Okay, which is what we had here. My Y was my ln of K, and my X was 1 over T. So then you just graph the equation that we calculated or derived on the last slide. All right, so we want EA. So I have my slope. So we're gonna use, so let's use this guy first, okay, to find my EA. And then to find the A, we'll use the second equation. So my slope was negative 9.29 times 10 to the third Kelvin. It's equal to negative EA over R. Remember, R is the same R that we talked about in this slide. Same R. So that's our gas constant. So the R that we're going to use is the 8.314 joules per Kelvin mole. So to solve for this, we just multiply our R over, and we get negative 77.2 times 10 to the third. The kelvins are going to get canceled, and we get just joules per mole. It's equal to negative EA. So if I want positive EA, if I want positive EA, I'm just going to divide the negative over, so I'll get a positive. But I also want my EA in kilojoules per mole. So if I want it in kilojoules per mole, I need to convert this. So let's do this. Let's divide that over. So now my EA is positive 77.2 times 10 to the third joules per mole. I don't want joules. I want kilojoules. Kilo is 10 to the third, so that goes on the bottom. So these 10 to the thirds just cancel. So what I find is that my activation energy here, my EA, is going to be 77.2 kilojoules per mole. So that's my first part. And it's finding the activation energy using the slope. All right. The next part is to find the frequency factor. That's my A. And we know that the intercept is equal to ln of A. So if my intercept is 23.85, and that's equal to ln of A, we have to get rid of this ln. We can't just divide by ln. So remember in class I had you pull out your calculators and look at what the inverse or reciprocal of ln is? And so on the calculator it says E. So to get rid of the ln, we raise both sides to the E. This cancels. So it's just E to the 23.85 is equal to A. But you can't just leave it like this. I want you to actually do the math, plug that in your calculator, and A is going to be 2.28 times 10 to the 10. Now, unit-wise, A ends up having the same units as K, but in this case, we aren't exactly sure what the units of K are, and so I'm fine if you want to just leave it as a number. You don't have to worry about the units for this guy. Okay, so that's determining the activation energy and figuring it all out if I have a graph. But most of the time, that might be like the lab way of doing things, but most of the time the way that we're going to find EA is, we have an initial and a final condition instead of just having a graph and trying to go through all that. So the equation that you're going to use the most is a combined Arrhenius equation. So my combined Arrhenius equation is helpful when I have like an initial and final condition, but it's also really helpful if we do not know the frequency factor. A lot of times in these problems, we don't really know what the frequency factor is. We don't know, is it going to be like only 1 out of 4 times that the orientation is going to be correct? It's kind of hard to predict that, especially in a chemistry reaction. And so what we want to do is we want to have the activation energy kind of rewritten so that I can solve for it without having to have A. So this is the combined Arrhenius equation, and it looks very similar to your Clausius-Clapeyron equation, where over here instead of K's it was P's. It's very similar. Clausius-Clapeyron, these were P's, and this was your enthalpy, and then the rest was the same actually. So K's are still your rate constants. This just might be for the initial, for the 1s, and the 2s might be just for your final condition. EA is still the activation energy that we've been talking about. R is your gas constant. If this is energy, this is going to be the one that has the energy, so the 8.314 joules per Kelvin mole. Now, this is in joules per Kelvin mole, so your Kelvin's going to come with your temperature, so your activation energy is going to be in joules per mole, not kilojoules. So you may actually have to convert your activation energy before you can plug it in. And then T is your temp, and because R is in Kelvin, your T must be in Kelvin. Okay, so we need it all to match up. All right, let's do a problem. So determine the activation energy. The rate constant for a particular first order reaction is given for 3 different temperatures. Using the data, calculate the activation energy for the reaction. So what am I looking for? I'm looking for the activation energy in kilojoules per mole. That's what I'm looking for in this problem. Okay. Then we want to know, okay, if that's what I'm looking for, what did they give me? Okay, so they told me it was first order, and they gave me 3 different temperatures and 3 different Ks. So I got a bunch of Ks and Ts, and I'm looking for activation energy. So right now there's only 2 ways that I can find activation energy. I can find the activation energy from a graph and its slope, or I can find the activation energy, I apologize, there's 3 ways you can find it. You can find it from the slope, you can find it from the equation that we did at the very beginning of the class, from this guy, or you can find it from my combined. Now, let's think about it. In my problem, did they give me the frequency factor? So let's go back and look. Did they give me the frequency factor, the A? No. And they didn't really tell me anything for me to figure it out. So if they don't directly give me the A, or if I'm not solving for A, you're not going to use this equation. You only use this equation if you have A, or if you're solving for A. So I don't have it. Okay? Then, am I going to use this guy, the slope? Well, they'd have to give me the slope. They didn't give me the slope. So if they don't give me the slope of a reaction, and they don't give me the A, then it has to be this guy. It has to be my combined Arrhenius equation. All right, so now that we figured out the equation that we're going to use, K2, K1, negative EA over R, 1T2 minus 1T1. Okay, now we can plug things in. I only need 1T and 1K. It doesn't really matter which ones I use. I only need 1 temperature, and 2 temperatures and 2 Ks. In my chart, they gave me 3. So it honestly doesn't matter which ones you pick, you just need to pick 2. So for me, it just seems easier to pick the first 2. Okay, so I'm gonna pick the first 2, and I'm gonna say that the 2's will be this one, and the 1's will be this one. Let's make the first one, and the second one 2. All right, so let's plug it in. ln K2 is the 6.1 times 10 to the negative 2. K1 is 2.9 times 10 to the negative 3. I'm looking for EA. R is my gas constant, 8.314 joules per Kelvin mole. T2, T has to be in Kelvin. It is in Kelvin. So that's gonna save me a lot of time. I don't have to go through and convert it or anything like that. The second temperature was 450. The first temperature was 400. All right, so let's simplify this. So let's do this K divided by this K is gonna give me 21.0345. Okay. And my units cancel because this was 1 over a second, this is 1 over a second because it says so in my table. So they cancel. Then 1 over this and then 1 over this. If you want these numbers, 1 over 450 is 2.22 times 10 to the negative 3. And 1 over 400 is, 0.0025. So you can either put it in your calculator in one fatal sweep, or you can do 1 for 450 gives you this number, 1 divided by 400 gives you this number, and then subtract those. So when you do 2.22 times 10 to the negative 3 minus 0.0025, that gives you negative 2.778 times 10 to the negative 4. All right, so now we have that number. So then we want to simplify again. Make some room. Okay, so to simplify again, let's simplify the ln of 21.0345, and that comes out to be 3.0462. Then we could do this divided by this. So let's do our negative 2.778 times 10 to the negative 4 divided by our 8.3. And that's going to give you times negative 3.3411 times 10 to the negative 5. All right, so we want to get EA by itself. So we want to move that number over. But instead of moving the negative over, we see that this is a negative right here, and this is a negative. So it ends up being a positive. So when we move this over, let's just move positive 3.3441. So this number divided by this number gives me an EA that is equal to 91173.56. And because this was in joules, down here my R is in, this is in joules per mole. But we said we wanted kilojoules per mole, not joules per mole. So I got one more step. Joules go on the bottom, kilojoules go on top. Kilo stands for 10 to the third, which is on the opposite side, so on the bottom. So this moves my decimal over 3 times, so I get 91.17 kilojoules per mole. And that's going to end up being my activation energy. All right, so we're going to stop here. And I'm gonna make another video just so that you have a couple of different short videos instead of just one really long video, but you're still gonna have 50 minutes per day that you need to watch. So don't think you get less per day now. All right, good luck.